Guys, welcome back. So in today's video, we're talking about equilibrium forces, right? Basically treating basics of this, right? The theoretical aspect generally, so that whenever you meet or encounter a problem, an examination that requires critical thinking, right? You'll be able to answer question under this. All right, let's dive in. Okay, the outline, right? The outline of what are we going to be discussing in this video? First, I will discuss the basic concepts, that's the foundation, right, of this topic, which are forces, unbalanced and balanced forces, and basically the first law of motion, right? The condition that was met for equilibrium to take place, the types of equilibrium we have, the cases of equilibrium, right? The force, the moment of force, moment of couple, right, and the difference between both of them, right? Okay. All right. So what do you understand by force? First, you should know by now that force is actually a vector quantity, right? How do we know it's a vector quantity? Reason because it acts in a particular direction. Let's assume we have a box here, right? Something of this nature. Right? If we apply for this direction, we expect it to move here, right? So force act in a particular direction. So force is a vector quantity, and it is defined as a push or pull on acting on an object. Okay, so as I proceed, you hear me often say net force. Which is this net force? So when I say something like this, what do I actually mean? Okay, now if you remember in our previous video we talked about friction, right? That there is actually an inherent resistance between this box and the surface in contact, right? Is actually inherent, it's always present, more like, right? Okay, good. So depending on the magnitude of this force, right, this object can move or might not move. It might move and it might not move, right? If this force, which is the frictional force, and the applied force are equal, so if F is equal to Fr, which is the frictional force, you expect this object to be static in it. All right, so net force is simply Fn equals to F minus Fr. So if F is greater than Fr, that is frictional force, you expect a motion to occur. But if they're equal, like if this is 5 and this is 5, that the net force is what? 0. So net force is simply the combined effect of all individual forces acting on an object, which I have just demonstrated using the object here. Alright, balance forces. In short, the name says it all. I don't distress myself explaining the details. Right? When it does say balance, it simply means that in the object, in an object, right? Let's say a box now, there are balance forces, right? So that's the scenario that has been used, right? Good. So that means the upper force is more or less equal to the downward force, the left force is equal to the right force. Yeah. So now balance forces occurs, right, or are forces, or when occurs when the total force acting on an object cancels out each other, right? If for instance this 6 Newton and this 6 Newton, this 8 Newton, this 8 Newton, what we have here are balanced forces. It must not necessarily be the same, right? It's not a must, I get it, but the net force of this is what? 0, right? Balance forces is achieved, right? So since the net force, this net force, which I can also say is summation F, that is the combination of all force acting on that particular object, is equal to what? 0. So if such a thing happens, do you expect this box to move? Definitely not. It will continue to be in a state of rest. In a state of rest. Is that clear? All right. Okay. Next one. is about unbalanced forces. What do you understand by unbalanced forces? So, based on what I said in the previous slide, that unbalanced forces, all the all the forces involved must not necessarily be the same, but the cancel of each other, resulting in a net force of 0. But in unbalanced forces, the net force is not actually 0. I get it, because motion is registered. Okay, let's say we have a ball here, and I kick that ball, most probably. Right, you expect it to move in forward direction. Right. Now, remember that there are forces acting opposite the direction in which I kicked. One is the resistance from the air, right? Friction, that is frictional force, right? But it's not actually strong enough to prevent this ball from moving. So in that kind of scenario, we have an unbalanced force. Now, the net force, I come again, the net force acting in an unbalanced force is not equal to 0. I get it. So, what are the effects of unbalanced forces? There is always a change in position. The object registers a motion, just like this example which I used using a football. Right, this change can be an acceleration, maybe, right, or deceleration. Like if a ball is coming towards me and I want to control the ball and score a goal, right, definitely deceleration will come into place, because on its arrival it's actually what accelerating, but immediately I chest it, right, or I stop it, I control it, it decelerates immediately. I get it. So it's due to unbalanced force. If the force were not balanced, right, I will not be able to stop the ball, and I might be displaced. I myself might be displaced. I get it. But due to the fact that the force which I applied to stop this ball from moving, right? So more like that. Okay. So the idea of equilibrium, right? So let's just get things straight here now. So if the size and object or the forces, right, or if the size and direction of the forces acting on an object are exactly balanced, right, then there is no net force. I've said this over and over again to tell you that it's a very good point. Right, there's no net force acting on that object, and that object is said to be in equilibrium. So equilibrium means when all the forces on an object are balanced. Yeah, right. All the forces acting on an object are balanced, right? So when there is net force, right, that object is said to be in equilibrium. And from Newton's first law of motion, what does it state? That an object will continue to be in a state of rest except an external force is being applied, right? So this ball, right, which is being kept in a state of rest by frictional force between the ball and the surface on which it lies, right? In that kind of case, it's actually in an equilibrium. It's actually in equilibrium. And Newton's first law is largely related to what? Equilibrium. All right. So some of the facts you have to know about this. So when all forces that act on an object are balanced, then the object is said to be in equilibrium. If you know you don't learn anything today, learn this. When all forces that act on an object are balanced, then the object is said to be in equilibrium. Is that very clear? Okay, the forces are considered to be balanced if the right force. So let me demonstrate this again. So let's have a box of this nature. If the right force, right, are equal or balanced by left force, and the upward force is balanced by downward forces, right? In this kind of case, we say this object is in equilibrium. All right, equilibrium of forces proper Now we're entering into the real task, the real job. Alright, coming over again, equilibrium is simply a condition whereby the resultant of the net force, right, acting on an object is equal to 0. So net force is equal to 0 in equilibrium, right? Good. So it is a state of an object where it remains at rest or maintains constant velocity. I know you are telling me, oh wow, constant velocity, how come? It's related to equilibrium, but we are getting there, right? So what are the types of equilibrium we have? We have basically two types of equilibrium, right? One is the static equilibrium, and the second is the dynamic equilibrium. No big deal. Exactly what these names mean literally is what each equilibrium talks about, right? So there are for static equilibrium now, we have what do you understand by static equilibrium, right? Right? Try. Type in the comment section. Now, static equilibrium is a state, right, of an object when it's at rest or remains at rest. Like it's when it's at rest or remains at rest. So in static equilibrium, the key point to note is that net force is 0. No big deal. Net force is 0. Static at rest. Static at rest. The net force is 0. And mind you, most of the example I've been using is ball on the surface and lights like that. It will not necessarily be on the surface, right? It can be vertical, it can be horizontal, right? It can even be like this, as long as all the forces are balanced. Like for instance, if this the horizontal part, right? This can also say to be in static equilibrium. Yes, if the forces are balanced. Now remember that the force of gravity is pulling this structure downward, right? But if I tie a string probably to the wall, right, and keep it stable, right, there is also an opposing force making this what stable. This is understandable. You can use candle for example, and basically if you place a cylinder, something maybe like matchstick on the table, you expect to see it in that part. I get it. That these are the result of what static equilibrium. Now the next one, dynamic equilibrium. Dynamic means something changing. Dynamic, literally, dynamic means something changing. Okay, now this dynamic equilibrium is actually a state of an object, right, which is said to be in equilibrium, but is undergoing constant, or it remains at constant velocity. So now, no big deal. Let's just listen. Now, in dynamic equilibrium, right, the object is said to be in equilibrium normally. I get it. But this object is not at rest. I get it. Like this object is not at rest. It's actually moving, but it's not accelerating, right? So this object is not accelerating, is not at rest, but has constant velocity. Like for instance now, if it covers equal distance in equal time interval, right, then that object is said to be undergoing what? Constant velocity, right? Constant velocity. So net force in dynamic equilibrium is still 0. Equilibrium, as long as you are talking about equilibrium, the net force must be 0. I get it. Because if the net force is not 0, then we expect the object in question, which I said earlier that it's undergoing constant velocity, to accelerate. Now, constant velocity is different from acceleration. I hope that is clear, right? Okay, now key takeaway is that in dynamic equilibrium, yes, net force is 0, right? This object in question is not at rest. So it's not as if the ball, let's say ball is on the surface. No, this ball might actually be moving. I get it, but it's moving at a constant rate. I get it. So that's exactly what constant velocity is trying to talk about. Right? So it's moving, just like I said here, that constant velocity can include moving in a straight line or at a fixed speed, or rotating around an axis. So if like a fan, for instance, right, if a rotating fan, oh, I'm not good at drawing, sorry. So a rotating fan is actually in a dynamic equilibrium. If you're not to be in a dynamic equilibrium, immediately on it, you are at risk, definitely, because it can exceed where it is and probably fly out. I get it. So it's actually in dynamic equilibrium in that point. All right. So cases of equilibrium, right? So now we now understand what equilibrium is all about. We now understand the various types of equilibrium that we have. Now, this equilibrium are being achieved in several ways, right? Through several ways. All right. The first one which we'll be starting with is equilibrium of parallel forces. Again, what do you understand by this, right? What do you understand by this? Without thinking much, what do you understand by equilibrium of parallel forces? All right, just like I've stated here, equilibrium of parallel forces refers to a specific situation where a rigid object remains at rest or maintains constant velocity when acted upon by multiple parallel force. So let's assume I have a block. This is a block, and I apply force in this direction, this force in this direction too, right? And apply, let's say, 50 Newton, and also this 50 Newton. Okay, so I expect this wall to remain at this same point. Yeah. So in equilibrium of parallel forces, there are certain conditions that helps us, that tells about okay, fine, this object is actually in equilibrium. Let's assume this is 20 and this is 10, this 10, and let's say this is the fulcrum. Let's say the fulcrum is here. This is just an arbitrary. This, let's say the fulcrum is here, right? Let's assume something like this. So in this part, this and this will cancel out. But does this and this cancel out? Not really. They don't. 2010. They don't usually cancel out. But I'm going to introduce something to you right now. Now, it's possible that the net force will still be zero. I get it. Because parallel forces does not necessarily mean that they're acting in the same direction. They are parallel, but not in the same direction. So now, the condition that must be met for you to describe an object, or to ascertain that an object is under equilibrium of parallel forces, is that the sum of all the forces acting on that object must be zero. Hence, that equilibrium must be zero. Right? The sum of the moment of all forces about a point must also be zero. Okay, here's what it means. Now, moment of force, though I'm coming to that, but let me just introduce it. Moment of force is what force times perpendicular distance, right? Perpendicular distance. Okay, now it means that from here to here, I'll say 10 times, let's say here is x. So 10 times x is equal to 20 times this, let's say this y. So 20 times y. There's a high probability that this is a smaller value and this is a larger value, making each of them equal, right? Let's say this is 1. Let's say y is 1. So we have 20 times 1 centimeter, and this is 10 times 2 centimeter. What do you expect? They will end up becoming what? 20 Newton or 20 nm equals what? 20 nm, that Newton meter. Making it what? The sum, right? So now note this: the net moment must be zero, and the net force must be zero. That's all for parallel forces. But now let's dive into moment of force. Okay, let's get exactly what moment of force. I just introduced it briefly there, right? Okay, now moment of force refers to the turning effect of a force acting on an object about a specific point. Now, forget about the big English, the grammatical words used here. Now, imagine yourself opening a door, like the handle door that looks like this. So when I want to open the door, I apply force in this direction. So it moves. It now becomes something like this. Am I correct? So it moves in this direction, right? So we notice that this point remains more or less at rest at a specific point. I get it. So this is the fulcrum, right? So while this point is the force, So the distance between the fulcrum and the applied force is the distance, the perpendicular distance. Exactly, the perpendicular distance. Good. So moment of force is trying to describe the turning force. Okay, now if I apply 20 Newton, okay, how will this thing turn? If I apply 100 Newton, what will be the effect? That's exactly what moment of force is trying to explain. That moment of force is trying to explain, right? So now it essentially measures how much a force can cause an object to rotate, right? And just like I've said before, that the formula is what? Force times distance. So as I told you, that tug is equal to what? Force times perpendicular distance. Okay, now it's not in all cases that you have the force at 90 degree to the perpendicular to the distance, right? Sometimes it can be at an angle, something like this, right? Let's say this is the fulcrum, right? So this is an angle, so it can be in this manner. I get it, but just use this in any case, in any scenario, right? Which is what? Sine theta. So if here was 90, it was 30 degree, you're going to impute it here, which was 90 degree, you expect it to be 1, right? So just ensure you remember the formula. Tug is equal to force times perpendicular distance times sine theta. Now depending, sometimes you might be told to calculate for more than one tug at a particular period of time, right, on the same machine or the same object, right? So now your orientation, that is your it can either have a minus, right, or a plus sign in front of it, just like when you are resolving vectors. I get it. Now when you're going clockwise, right, when you're going clockwise, that is like this, right, you assign a what? A negative sign. I get it. You assign negative sign, but when you're going anti-clockwise, you assign a positive sign, right? So do not forget that. All right, so what are the key points you have to remember in moment of force? You should know that is actually the product of force and the perpendicular distance. You should know that by now, right? And the vector quantity. Now remember that work done is what's for work done? Force times distance. Not perpendicular distance, but force times distance. You can, without, if I move the perpendicular from moment of force, you might actually think that it's the same formula, but it's not, right? So moment of force is a vector quantity, while work done is a scalar quantity. I get it. Now couple produces rotational motion. Now I'm going to come to this in detail, but you should know that couple produces rotational motion, right? Good. And whenever you are asked to solve question on moment of force, take one point at a time, because sometimes it could get, what if we have something like this, we now have something like this, right? Maybe have this like this again, right? Take it at a point, right? Take each moment of force at a point, not trying to get everything at once. It might become so complex, right? So at the point of application of force, right, you should take it at that point. And now what's the SI unit? Now the SI unit of force is Newton, as we all know. SI unit of distance was meter. So the SI unit of moment of force is what? Newton meter. Exactly. All right, so the next one, which is differences between moment of force and moment of couple. I've seen this several times, and students tend to mix them up most of the time, right? Okay, now before I even go into the details, now I actually told you I explained force to you. Now let me explain couple to you. Okay, now couple means something that maybe couple to, like couple, maybe something related to, right? If you have that assumption, you are correct. Now look at what the couple looks like here. Look at what the couple looks like here. It looks something of this nature, right? This is the force here acting here, and this is the force acting here. So for couple, I define couple as a system that consists of two equal and opposite forces acting with two different but parallel line of action. Now, two different but parallel line of action. This line of action of this line of action of this, right? But it's what in opposite what direction. So two different parallel lines of action. Now, moment of couple is also known as torque. In short, torque can be assigned to both moment of couple and what moment of force, right? You shouldn't disturb yourself on that. All right, now let's go into details now. Okay, moment of force, common word again, is dependent on the distance, right? When we're solving question on moment of force, I tell you that it's force times force and perpendicular distance, something like that. I get it. So moment of force is dependent on distance from the pivot and magnitude of the force, right? Because of it's dependent on magnitude of the force and what and the distance. While moment of couple is the net effect of the two moments of force. Now, look at how a couple looks like, right? You can now actually say, okay, this is the fulcrum, this is the fulcrum, and that's the force, right? You take two of them, right? When you take two of them, you notice that we've neglected the distance itself, right? So now, when we are solving for moment of couple, what we're actually calculating is the net effect. Okay, what would be the end? What would be the effect of this coupled system? Okay, it will be rotational motion. Okay, it will remain in equilibrium. It will remain at rest, which is static equilibrium. I get it. Now, in moment of force, right? Torque depends again. I'm coming again. Torque depends on the axis of rotation, right? It depends on the axis of rotation and point of application, right? If I apply force here, that at this point, I don't expect moment of force. I get it. So it depends on the point of application of force, right? It depends much on that because the distance matters. The distance matters and the force also matters, right? Now, if I were to have something like this and apply a force, maybe coming in this direction, you expect it to now be in this direction, right? To now be in this direction. Let's assume it has something of this nature, something here. So it has actually moved from here up to this distance. So it can produce translational acceleration, right? It can produce translational acceleration. And if we continue moving this part, if we continue pushing this system, right, at some point it will definitely be in this direction, right? Good. Now it's producing a rotational effect. This rotational effect is balanced by this fulcrum, right, which I call in this my text by a proper single force, right? A proper single force. Now, what of moment of couple? What do you understand by it? Now you understand what couple means. Now, torque depends upon two forces. I illustrated it in the diagram. Drawing it again. Torque depends on two forces in moment of couple, right? It is independent of the axis of rotation, so it is independent of this part. The distance between them is more or less independent of it, right? It just depends on the forces involved. Does not produce any translational motion. Now, regardless of how I turn this, you don't expect this to now be in a new position. No, it must just keep on rotating. So what it's actually produced is a rotational effect. I get it. It produces a rotational or angular acceleration. Is that clear? Good. Now, the rotational effect can be balanced by another couple of equal and opposite. So here what I'm trying to say. Now, if I have something like this now, and this 5 and this 5 Newton, and also this 5 Newton, what I expect, you don't expect anything to move. It's going to be balanced. Like it's going to remain in this particular state. Is that very clear? All right. Equilibrium of non-parallel forces. All what we've been treating before are equilibrium of parallel forces. Now, what of non-parallel forces? When do we say, or when can we say an object or a system is under non-parallel forces? Now, for it to be under non-parallel forces, right, they must be coplanar. Coplanar. What is coplanar? They mean it must not on the same line, right? They must not be on the same line, or they must not be what? Collinear. Now, they must not be on the same on the same line. If we have something like this, you should know parallel forces. Is that clear? So they must what? Be coplanar. They must be concurrent. So they must be acting acting or passing through a particular point. So let's say this is the object, it may be passing through a particular point, right? It must be passing through a particular point, right? Not passing through a particular point. And with this, I can actually resolve it to become what? I can actually represent it using what? Polygon of forces or triangle, and the triangle law, right? Triangle law means, okay, this A, this can be A, right? This can be B, right? Depending on their orientation, right? If this were something like this, sorry, don't mind my diagram. I can now say, okay, this A, this B, and this C, right? So this A, this B, and this C, right? So if I were to represent it this way, since this C, here also be what? Be C, here will be what? B, and here will be what? A. So what equilibrium of non-parallel force is trying to say is that it can be represented using what? By applying the law of triangle, the triangular law of forces. Do you get that? All right. So what of equilibrium of a rigid body? Now, I like relating it to stability, right? Whenever we're talking about equilibrium of rigid body, we're basically relating it to what? Stability of object. I get it. Okay, if you place bucket on the floor, what are the probability that it's still going to be in that state of rest? I get it. There are certain positions where you place a rigid object, which it won't be stable at that point, at that position. I get it. Equilibrium forces what? Encapsulate this term. Is that very clear? So, just like I said here, even though a body might be in equilibrium, its behavior can vary depending on how it reacts to slight disturbance. Now, if you place your phone on your desk, right? If you shift it, most probably it might not break, but there's a certain position or certain orientation which your phone might be in that any slight change, any small disturbance will lead it to fall down. We actually shatter the phone. Now, what is stability? When you hear stability, what does it mean? Now, stability refers to the tendency of a body in equilibrium to resist a change in its position when subjected to small external force or displacement. Is that clear? Now, there are three types of stability, right? Or equilibrium of rigid body, right? One is stable equilibrium, the second is unstable equilibrium, and the last is neutral equilibrium. Now we're going to take each of them single, we're going to treat each of them, right? So you'll be able to understand it very well. Now, stable equilibrium, you know why I like physics, right? Just calm yourself down and relate with it like your brother. Now, stable equilibrium, we now understand what equilibrium is. What is stable? Stable equilibrium means that, okay, this particular object, when it shifts, it still remains at that position, like it's still trying to stay at that particular position. I get it. Like now, if you say an economy is stable, it does not mean that that economy is not subject to change. It actually changes, but if it changes, it goes back to its normal position. If it changes, if any external force or whatever affects the economy, it goes back to that initial position. I get it. So it's still related to what? Stable equilibrium. Now, in this case, if a small displacement occurs, the body will return to its original position, equilibrium position. Do you understand that? Right? Okay, now let's imagine a bell, something like this. I get it. If I shift this bell, right, it will still remain, it will not change that much, right? It will still remain at this position. Do you get that? Now, or if I tilt it a bit such that it becomes like this, only minimal places in the floor, right? At this point, it will still, if I remove the external force, it will still remain, it will still come back to this normal position. Is that very clear? Now, what do you have to note about stable equilibrium? Now, in stable equilibrium, forces tend to decrease the displacement when slightly displaced. Now, I gave you this example. That, let me change the, okay, now I give you this example here. right? Let's assume the force is swinging in this direction. Now, if I tilt it in this direction, right, there are resisting forces. Some forces are acting here to ensure that it continues to remain in this equilibrium state, right? To ensure that the bell continues to remain in this equilibrium state. So now, in stable equilibrium, there is what? A restoring moment, right? This we can take it to be the fulcrum, right? Why here all these parts are what? The restoring what? Moment. So it has a restoring moment. And forces that tends to decrease, forces are present which decreases the displacement when slightly what? Displaced. Is that very clear? Now, this particular statement which I said, moment of the weight or force of gravity is greater than the moment of the action about the edge. Now, look at this. Look at this. Let me draw it again. Don't mind my drawing, no verse here. So we have something of this nature. What this statement is trying, this number 3 statement is trying to say is that there is actually the weight looks as if acting more on this side. I get it, because the force of gravity is now adding to its weight. So the moment of the weight or force of gravity is greater than what? The moment of action about this edge here. I get it, about this edge, the moment of force is greater in this place. So if the moment of force is greater here, what do you think will happen? It will go in this direction, isn't it? Exactly. That's what this statement is trying to say. Moment of the weight or force of gravity is greater than the moment of the action about the edge of tilt or greater about the base. Alright, so this is CG, center of gravity. Vertical through center of gravity rises and center of gravity falls inside and after the displacement. Now, let me draw it again. If it's actually displaced to this particular position, the center of gravity rises, and also what? It rises, right? Let's say if the center of gravity was here before, it becomes somewhere like here, and then it shifts to this part. So the center of gravity rises, but when it comes down to normal position, it what remains. When it goes back to its normal position, that is, it falls. The center of gravity falls, right? Okay, now unstable equilibrium. What do you understand by unstable equilibrium? Now, if a small displacement occurs, the body will move away from its original position and not return. That's what stable equilibrium is all about, right? That's what unstable equilibrium is all about. Since it will, since now you just have to be apply logic here. Okay, since we apply force and it goes to a new position, not only a new position, it does not return back to that former state, right? Just like in the illustration of using a bell. Now you will notice that there is no, because of the reason why such a thing is possible here, because there is no restoring moment. I get it. There is nothing that is okay bringing it back, right? Okay, I like using the economy of Nigeria for an example, right? If, for instance, there are several other things that contribute to the stability of our economy, let's say agriculture. If oil is not performing well, then we expect agriculture to take over. I get it. Now, if we tilt an object, right, and it falls down, it simply means that the forces that are preventing such a movement, such displacement from occurring, is not strong enough. That's just the case in unstable equilibrium. In unstable equilibrium, no restoring moment. No restoring moment. And also, the moment of the weight or force of gravity is less, right, than the moment of the action about the edge of tilt. Forces tend to increase the displacement. Now, look at this. If I tilt, if it's like this, if the bed is like this, right? If the bed is like this, you don't expect it to return to the normal position of like this. You don't expect something like that, because it's the force that is supporting this motion, supporting this displacement, is so great. Imagine, it's so great. I get it, that it now lies in a new orientation. That's why I said here, force forces tend to increase displacement when slightly displaced. This is why a body does not return to its original position after displacement. Is that very clear? Okay. Vertical true center of gravity falls outside the object after displacement. Now, center of gravity is in this part. I get it. But after displacement, the center of gravity falls outside the base. It lies outside the base of this object. Do you get it? That's exactly what I'm trying to say. The next one, neutral equilibrium. Neutral equilibrium. Now, what do you understand by neutral equilibrium? It simply means that it can move to another position. Now, I like using a cone, for example. Let's assume a cone is like this, right? If I apply a force, it can come into this direction. It does not have any problem. Has the orientation really changed? No, the orientation have not changed. If it were to be like this, and then it becomes like this, then you can now say, okay, this is what unstable equilibrium, right? But since it has always been like this, we call it neutral equilibrium, right? It does not return to that same position which it were before displacement, but its orientation remains the same. Do you get it? Now, in this case, a small displacement will not cause the body to move in any particular direction. The body will remain in a new position. Alright. Force tend to keep the body at the same position when displaced. This is why a body does not change position. It's always the same. It's always what? The same. Moment of weight of force of gravity is equal to the moment of action about the edge of the tilt. So in neutral equilibrium, the moment of force of gravity, right, is equal to the moment of action about the edge, right? Good. Vertical. Now the center of gravity is going down this way, right? Now that's why they say vertical true center of gravity remains at the same position and CG does not change, right? Center of gravity does not change in neutral equilibrium. Is that very clear? Center of gravity does not change in neutral equilibrium. Now let's identify all this, right? If you have something like this is a cone. You have something like this. I have something like this. If you have something like this, right? Which one do you think? Which type of equilibrium is this? Stable, unstable, or neutral? Correct. Stable. What of this? Unstable. What of this? Neutral. Alright. So what is peculiar about this is just that if tilted, right, the center of gravity, right, lies within the base, making it to always return towards its previous position. But here the center of gravity lies outside, right, displacing this cone in an unstable equilibrium. For in this place, the center of gravity does not change. It always the same. It always remains at the same position. But here, you know that it at some point it becomes like this, but it always remains in what? In the base. That's why it will always return back to its previous position. Is that clear? Alright, let's recap. So we know that for force, force basically means the pull, right? The pull or push on an object. That is clear, right? Good. Okay. What of balance and unbalanced forces? What do you understand by that? I've explained it that balance forces, all the objects tends to maintain an object in equilibrium, and unbalanced forces, there is motion, there is acceleration or deceleration, right? Equilibrium forces, we've talked about that. Moment of force, you now understand what moment of force is, right? And you now understand the difference between moment of force and moment of couple, right? Good. Now, case of equilibrium, which I talked about, the neutral equilibrium, the stable equilibrium, unstable equilibrium, all that are under equilibrium of rigid body, right? For special cases of equilibrium, I said equilibrium of parallel forces, equilibrium of non-parallel forces, which I said for a body to be under equilibrium of non-parallel forces, it must be coplanar, right? It must not be linear, right? Yeah, so all that we've talked about. All right, thank you so much for watching this video. We appreciate your time here, right? More videos will be uploaded. I'm very sorry for some glitches which you experienced during the course of this video. We apologize for that. Thank you so much. If you are new here, consider subscribing, right? Consider sharing, like our video, right? And turn on the notification bell so that more videos, when we release new videos, you get access to it before anyone else. Thank you so much. God bless you. Bye.